Welcome back to Mathematical Statistics. I'm Mark Ledbetter. In this section, we are talking about order statistics. This is section 6.3 in the textbook, and this is lecture 3. So I hope you enjoy the video. All right, we've talked about the topics in the PowerPoint slides for this section. So let's talk about the objectives for this section. So when you get finished with this section, we want you to be able to explain and define an order statistic, find the PDF of any order statistic, compute the mean of an order statistic, and find quantiles and percentiles. And again, this will be using the distribution of the order statistic. And finally, we want you to be able to manually create a QQ plot, which is a quantile plot. And these are used to visually verify if a sample is from a certain distribution or a suspected distribution, if you will. So to start this, what is an order statistic? The best way to answer this is maybe to give you an example. So we have a random sample of n equals 7, and the order of selection is given below. So this is how we obtain these numbers. We randomly chose, and this would be x1, this would be x2, x3, x4, x5, x6, and x7. Now, to plot this, this would be x1, 2 would be x2, 6 would be x3, 4 would be x4, 3 would be x5, 1 would be x6, and 7 is x7. Well, our order statistics, we're going to call those yi. And so in order statistics, we'll have y1 as the first order statistic. It's going to be less than or equal to y2 and on up to y sub n. Okay? So in this case, y1, actually we're going to use lowercase letters for the actual values. y1, y2, y3, y4, y5, y6, y7, and y8. Okay, or I'm sorry, there's no y8, is there? There's no point there. All right. So these are in increasing order. That's what we do with order statistics. So this seems like a very simple concept, and this part of it is. But this can get very complex very quickly when we start talking about the distributions and probabilities to do with this. Okay. So you might ask, why do we want to study order statistics? What's important about these that we want to take time out of a mathematical statistics course to cover something that seems so simple? What's the deal? So the median is uses order statistics to calculate it. The range is equal to yn minus y1. This is the nth order statistic, which is the max, minus the first order statistic, which is the min. Okay? And then percentiles and quantiles are calculated with this. And finally, the distributions of order statistics are important in many applications. And we'll see an example of this in the section 6.4 for the maximum likelihood estimator. We'll see where one of the maximum likelihood estimators is y sub n, the nth order statistic. Okay? And so to find the mean or variance, we have to find to find the bias of the MLE, we have to know the distribution. We have to be able to find the mean and the variance. Okay. And so in this course, we are going to limit ourselves to the continuous distributions. Continuous distributions are generally considered to be easier than the discrete distributions when it comes to these distributions and what have you for order statistics, because with continuous distributions, there's set rules and formulas that we can use, whereas with discrete, you have to think through the problem from scratch basically each time. Okay, now because we are going to consider continuous distributions, note that the probability of a tie is 0. So the probability that yi is equal to yj equals 0 for a continuous distribution. Now, I want to point out, practically speaking, that because of the precision of our measurement devices, we do get ties in practice. And it's because of rounding. So it's a rounding error. So, but with that, we end up with numbers we can't discern between, because they're after we round, they're the same number. So if the probability of a tie is small, whatever small means here, small enough, the distribution theory that follows will hold approximately, whatever approximately means. So these are things that in practice you would have to do some calculations to see how much error there is in the calculations. And so that would determine if it's small enough and if the approximately holds well enough. All right, so I didn't want to gloss over that very vague statement by our authors. Okay, so let's talk about the definition of an order statistic. Let x1 to xn be the observations of a random sample of size n from a continuous distribution. The order statistics are then denoted as y1 less than y2 less than yn. Notice again, because they're continuous, we do not have the equal sign here. Okay? And we're going to call y sub r the rth order statistic. And it is the rth smallest value of the random sample, where r is from 1 to n. Okay, so y sub r. Now, some textbooks use, say, x1 with parentheses around it to show the order statistic. So if you look at a different text, look for their notation so that you can, where they define it, so that you can know what notation you're looking at. Now, the CDF of the rth order statistic is derived using the binomial distribution. And it's a lot easier to understand this if we see an example, which is what we're going to do now. So this example, x1, x2, up to x5, let that be a random sample from a distribution whose PDF is f of x equals 2x, x between 0 and 1. Now, when we see x is between 0 and 1, we think of which distributions this could be, and we think, that could be the beta distribution. And in fact, it is a beta distribution, a very simple one, where alpha is equal to 2 and beta is equal to 1. Sorry. Okay. So let y1, y2, up to yn denote the associated order statistics. That means associated with the x1 to x5. Okay, and it was y1 to y5. I don't know if I said n or not, but I meant 5. Okay. So the first thing we want to do is we want to find the probability that y is y4 is less than 1/2. Okay? So y4 is less than 1/2. So notice, so this is A, notice that for the set y4 less than 1/2 to occur, at least 4 of the random variables x1, x2 to x5 must be less than 1/2. They have to be less than 1/2. Why? So let's look at a little picture. This may help you. Whoops. Of course, I can't draw a straight line. So, all right. So the range is 0 to 1, and here's 1/2. Now, if y4 is over here, then at a minimum we have y3, y2, and y1 over here because they are less than y4. If I look at this statement here, if I look at this statement and look at y4, if y4 is less than some number, then y3, 2, and 1 all have to be less than that. These are order statistics. So this is one case where y5, let's say, is not less than a half. But we can satisfy this set here, y4 less than a half, in two ways in this case. So what if y5 is less than 1/2, then we'd have y4, y3, y2, and y1. y4 is definitely less than 1/2. But if y3 is not less than 1/2, then y4 has to be above, and of course y5. So there's two different ways that this can occur. When y4 is less than a half, but y5 is not, and when all 5 observations are less than 1/2. Okay. So our solution starts here. Let the set x of I less than 1/2 be called a success. So we're taking this, the infinite number of possibilities for x between 0 and 1, here, our support, it's continuous, so there's an infinite number of possibilities that x can take, and we're breaking that down into two categories. X is less than a half, xi is less than a half, or xi is between 1/2 and 1. So two categories. We're going to call xi less than a half a success because that's what we're interested in. We want to know the probability that y4 is less than a half, and so we have to calculate out for each of these. The easiest thing to do is to calculate out for each of these xi what a half is, and then use the binomial. Okay? So the probability of a success is the probability that xi is less than 1/2. And we can figure this out using calculus. We take the integral from 0 to 1/2 of f of x, which is 2x dx. And when we integrate this, this is x to the 1, so we add 1 to that, we get x squared, and then that exponent, 2, we need to divide the whole thing, the whole function by that. So we end up with 2x squared divided by 2. These cancel, leaving us x squared from 0 to 1/2, which is 1/2 squared minus 0 squared, which is 1/4, which is 0.25. This is p. This is a constant. There's no x in this value, so p is a constant probability. Okay? Remember, it's a random sample. These are independent trials. So x1 to x2, x3, x4, x5, they are all independent. So they're independent observations, or if we consider repeating this as an experiment or trial, then they're independent trials. We're saying that we're going to do this 5 times, so n is 5, it's fixed. That is a condition of the binomial. We have a constant p, and then we have two categories. xi less than 1/2, and xi greater than 1/2, but less than 1, of course. So this is a binomial. A binomial. All right. So again, we said that in order for y4 to be less than 1/2, there's two ways that we can do this. y5 not less than 1/2, or y5 less than 1/2. Okay, so there's two possibilities. I think the easiest way to solve this is to let w equal the number of xi less than 1/2. And then we can write that f of w is equal to n, which is 5, choose w, p to the w, q to the n minus or 5 minus w, the binomial formula for the binomial distribution formula. And this is equal to 5w 0.25 to the w 0.75 to the 5 minus w, w equals 0, 1 up to 5. All right. So I want the probability that we have at least 4 of these. We want y4. So we want w at least 4, which is equal to the probability that w is equal to 4. That's where y4 is less than 1/2, plus the probability that y5 is also less than 1/2. And then I can just plug in, and I have 5 choose 4, 0.25 to the 4, 0.75 to the 1, plus 5 choose 5, which is 1, by the way, and this is 5. 0.25 to the 5, and then 0.75 to the 0, that's 1 as well, and this equals 0.015625. Here's our probability to part A. Now, part B, we want to know the CDF of y sub 4. Okay? So the CDF of y sub 4. So in general, for this example, the probability, let P equal the probability that xi is less than some value y, okay? Where y is between 0 and 1, right? So we're in the range of y, which is also the range of xi, okay? And so this is equal to the integral from 0 to y of f of x dx, which is equal to the integral from 0 to y of 2x dx equals x squared from 0 to y equals y squared. Okay. And so this is the probability that x is less than, xi is less than some value y. Okay. So the PDF of y4 is equal to, we'll call this G, the CDF. We want the CDF of y4. So let's look at the CDF, that's part B of y4. So G of little y is equal to the probability that y4 is less than or equal to y, which is equal to, now again, I have 5 choose 4, so we can have that y4 is less than or equal to 5 only, and y5 is not in this case. Or we can have that all 5, y5 is also less than little y. So this is going to be y squared, that's p, raised to the 4. And then I have 1 minus p, which is 1 minus y squared, raised to the 5 minus 4, which is 1, so I don't need to put anything there. This would be 5 minus 4, but that's 1. And when it's 1 as an exponent, we don't need to put the 1. So we won't. And then the case where we have 5 choose 5, and then p is y squared to the 5, and then 1 minus y squared to the 0. And I can rewrite this as 5 choose 4, y squared to the 4th, 1 minus y squared, plus y squared to the 5th, where y is between 0 and 1. And this is our CDF of y4. Okay? Again, this represents the probability of at least 4 successes out of 5. Okay, at least 4 out of 5 are successes, which is less than a half. Okay. Now for part C, we want the PDF. So the PDF, we're going to write this as G4 of Y, and that is going to be equal to G prime. So let's not put the 4, we'll just call it G of Y here. I don't remember what the book says, but I'm going to call it G of Y. And you could put Y4 here if you want to do that. It does make it messy. So we're going to say this is G prime of Y. And now I have to take the derivative of what I've underlined above. Okay? So I'm going to leave the 5 choose 4 out in front. And then I have to take the derivative of y squared, the y squared term. We're going to use the product rule, so I'm going to leave the 1 minus y squared alone at first, because I have to take the derivative of the first times the second, plus the derivative of the second times the first. So we've got the 5 choose 4, and then the derivative of y squared is going to be 4 y squared to the third, and then the chain rule, 2y. And then times 1 minus y squared, and then plus, I still have 5 choose 4. Now I leave the first one alone, y squared to the fourth. And then I take the derivative of 1 minus y squared, which is negative 2y, because it's to the first power. And then I take the derivative of the second term, which is y squared to the fifth. That's going to be 5 times y squared, and then times 2y using the chain rule. All right. Now, I'm going to simplify this in a specific way. I'm not going to simplify this like you might simplify this, because I want to come up with a general formula. So we're going to use some manipulation here that is in hindsight. We did this because we'd already seen the solution and figured out some things. So this is going to be 5 factorial over 4 factorial, 1 factorial. And then we've got times 4. And then we've got y squared cubed, y squared to the third. And then we've got 1 minus y squared. And then we have 2y, okay, in the end. And then it's going to be minus, because I have a minus here in this term. So it's going to be minus, and then we do the same thing. 5 factorial, 4 factorial, 1 factorial. And then I've got y squared to the fourth. And then I've got 2y. And then I've got, and then I've got 5 plus 5, and I've got y squared to the fourth times 2y. Okay. So now I've got this 4, and I've got a 4 factorial here. So I'm taking, so I've got this 4 factorial, remember, is 4 times 3 times 2 times 1. So we've got a 4 up here. We can cancel the 4. We'll end up with 3 factorial left, okay, on the bottom. So this is equal to 5 factorial, 3 factorial, 1 factorial, and then times y squared, 1 minus y squared times 2y. Okay, I missed the cube here, so it's y squared cubed, 1 minus y squared, 2y, and then minus, and here I've got, I can simplify this to 5. 5 y squared to the fourth, 2y, plus 5 y squared to the fourth, 2y. And these terms cancel out. And I am left with 5 factorial, 3 factorial, 1 factorial, y squared cubed, 1 minus y squared times 2y, and y is between 0 and 1, and this is my PDF. You might wonder why I'm not simplifying this. We will find out very shortly here. Okay, so this is my PDF, and so as I said earlier, it's easier to see an example of this, and then you know where the formula comes from. So remember that we said that the CDF of xi is equal to the integral from 0 to xi of 2t dt. So t squared x, from 0 to x gives me xi squared. X is between 0 and 1. So the same thing is true for f of y. F of y is equal to 0 to y 2x dx, which is equal to x squared from 0 to y, which is equal to y squared. So that means that this is f of y in here, and this is 1 minus f of y. And then the derivative, so f of x, so I could say, let's do it for y, then I can say f, so f prime, no, I'll start off with the CDF. So the CDF, f, whoops, wrong button. F of y equals f prime of y equals 2y. Okay? Y is between 0 and 1. So this is little f of y, the PDF. Okay? So I've got n here, n factorial. So I've got n factorial. And then I've got, let's see, n minus 2 factorial, 1 factorial. And then I've got f of y to the cubed, 1 minus f of y, and then little f of y. Okay. So here we have, I have written it out. I use y4s here, but I didn't use it up here, but I could put a 4 to all of these, and it would be fine to just to denote, to specify that we're talking about the fourth order statistic, y sub 4. And so now I can rewrite this as 5 factorial, and now I'll write 4 minus 1 factorial. That's 3 factorial, right? And then I can write 5 minus 4 factorial, and that's 1 factorial, right? Okay. And then I have f of y4, and this is a 4 minus 1, which was the 3, right? So not very clean. Let me clean that up. So let me zoom in and see if I can clean it up a little bit. All right. So 4 minus 1. So, and then we have 1 minus the CDF, f of y4, and this is 5 minus 4, and that was to the 1. And up here, this was to the 1, right? And then we have f of y, the PDF here, okay? And of course, don't forget your support of y. So now we're going to use this to come up with a general formula. Now, we haven't proven this. We're just saying we see a pattern here. And so this is not a true proof. This is a generalization, not really a derivation, but a generalization of what we're seeing. But we can use induction and prove this if we wanted to. Okay? So here is what we're left with. The formula for the PDF of y sub r is given by, so g of y sub r is equal to n factorial divided by r minus 1 factorial divided by n minus r factorial, and then the CDF of y sub r raised to the r minus 1. Okay. And then, is this r minus 1 or n minus 1? 4. Yes, r minus 1. Yep, yep. And then 1 minus the CDF raised to the n minus r, and then times the PDF, and y is on some interval a to b. Okay? So this is a formula. Excuse me for zooming too far down. So this is a formula that you want to have on your formula sheet. You're going to need it. So let me clean this up a little bit and write g sub y. And this is the PDF of y sub r is given by this formula. All right, that's it for this video. I hope you've enjoyed it. If you have questions, then please come to virtual office hours, and I'll be glad to try to point you in the right direction. If you need help before you can make it to virtual office hours, then by all means email me, and I'll do my best to help you through email, and I'll respond to you as soon as it's possible. Please take care of yourself so we can see you next time.